So it is my pleasure to introduce Alexios Polychronakos once again. So he's polymath, polyglot, and tireless speaker. And he is going to start his series called Nobel Prize Lectures from 2017 till the beginning of Nobel Prize award. So Alexios, please, 2017, LIGO, Discovery of Gravitational Waves.
Thank you. Thank you for being here again. I have to warn you that this is a lecture that I had to give at my home institution, the City College. It's a tradition that every year after the Nobel Prize is announced, a few weeks later, there is a presentation by somebody from the physics department on the topic, and this year was my turn. This talk is geared to physics undergraduates and people outside of physics with some general science knowledge, so it's going to be at a very low level, sophomoric basically. So don't be offended by what you're going to see here. It wasn't prepared with you in mind. Just sit back and enjoy the ride for as long as you wish, and please feel free to leave at any time. This is like an open session, right? Okay, so the Nobel Prize in Physics in 2017 was given to those three guys, Rainer Weiss from MIT, Kip Thorne from Caltech, and Barry Barish from Caltech. And according to the citation, it was for decisive contributions to the LIGO detector and the observation of gravitational waves. So we are going to remind ourselves how gravitational waves were born in people's minds, and eventually they reached the Earth and were detected and achieved this prize. Also, as a background, those two guys, as you know, are from Caltech. I had courses from both of them, so I can give you a little bit of personal taste. So, the long story is that Einstein first postulated or kind of proposed that there should be gravitational waves in 1916. After all, gravitational waves are kind of a natural consequence of general relativity. As waves go, they are peculiar in that they are everywhere, even in this room. They are produced by everything, even myself gesticulating in front of you right now, and they cannot be shielded by anything. There is no Faraday cage for gravitational waves. So why did it take so long to detect them? Well, we know why, because gravitational waves are very elusive. They were, as it turns out, very hard to pin down theoretically. They are very hard to produce in any reasonable amounts, copiously, and they are extremely hard to detect. So it really took a century from their inception to their detection. And here is a picture of City College in 1921 with Albert Einstein visiting. City College has the honor of being the first public institution in the United States where Einstein gave a lecture. He gave his lecture at City College basically one day before he gave a lecture at Columbia University in that visit. Right, so a posteriori, with hindsight, it seems obvious that there must be gravitational waves because after all, even special relativity tells us that there is action at a distance. So if gravity tells you that bodies influence each other through gravitational interactions, no matter what the physics, any change in the state of one body would have to influence the other body. That influence cannot be instantaneous, so it has to travel somehow, and that travel, that information transmitted will be a gravitational wave. And if they exist, they must most likely travel at the speed of light because there is no other natural speed at which they could travel, so they are ripples in space-time. And yet, it took Einstein and other people who worked on it a long time not only to fully fix their form in mathematics and physics, but also to even accept their existence. So it's part of the sociology of the field that I think it's interesting to physicists, so I will tell you a little bit about it. And of course, the obvious question is why? If Einstein couldn't figure it out almost immediately, what was the issue? So here is this simple Newtonian argument. If you have two bodies at a distance, I told you this is sophomoric, right? If you have two bodies at a distance d, they attract each other with a Newtonian force of this magnitude. And if you were to transport this body by a distance delta that decreases the mutual distance, the force should increase, and therefore the force on that body should increase as well. And that is the gravitational wave, that transmission of that of the information that this position changed, and that wave reaches the other body and increases a little bit their force. We can even calculate the increase of the force. It is the difference between this and that. And to first order, to lowest order in delta, it's this quantity which goes like 1 over the distance cubed. However, that's not quite the full picture, because nothing moves by itself in gravity. You cannot just say, I have this body and it moves like that. Everything moves because of some physical cause. So, for instance, if you had a body like that and you wanted to move it, it should be kind of fixed on a bigger body like the Earth. And then, because the Earth is so big, you say, I can move that other body. However, even if the Earth is very massive, if I move one body one way, the Earth has to backtrack because the center of mass of the system is fixed. So this happens. If this moves by delta, this will move by some capital delta, much smaller, and the two, of course, by the center of mass condition are related like that. So the total change of force on the other body is not only the part that comes from this mass, but also the part that comes from that mass, which is negative because that mass backtracked. You put them together, you use that condition, and you see that the answer is 0. So there is no additional force. There is no additional force that this body would feel in a situation like that, and therefore there is no gravitational wave to lowest order in delta. That we say in more modern language, it's a manifestation of the fact that there are no gravitational dipoles, and what I was trying to do here was to create such a dipole. So this gives us just a glimpse of the conceptual difficulties that, or conceptual issues that are in this field, a very elementary one, and that kind of mirrors to difficulties when you deal with a full general relativity. So let's start this intellectual trip from the very beginning. Dawn of knowledge. Anybody knows what is this? Yeah. I didn't think there would be many people who didn't know it until I realized that there are. So, okay. This is Stanley Kubrick's famous movie. Some of us grew up with this movie, all right? Okay, back to gravitational waves. The honor for introducing the concept of gravitational waves should go to the French mathematical genius Henri Poincaré, who in his treatise on relativity and waves, etc., said that the same should be true for gravity, and he called them ondes gravifiques, which means gravitational waves in French. Now, Einstein, of course, even before he developed the final version of his general theory of relativity, was kind of sure that there are these waves for the same reasons that we expanded before. And in fact, in a letter to Max Bohr in 1913, said there must be gravitational waves traveling with the speed of light. And yet, in a letter to Karl Schwarzschild in 1916, that means right after he had the final formulation of general relativity, said there are no gravitational waves. This is probably related to the non-existence of a gravitational dipole. Right. Einstein actually had done calculations, and it turns out that in these calculations he had used a gauge. G is the metric, is the volume factor, so the space-time volume factor, so it's the determinant of the space-time metric. And because you can change your metric, he had used this gauge in his calculations to simplify things. But he had done that inconsistently. He had used the gauge without taking into account that he had fixed the gauge in some other part of the calculation, and that eliminated gravitational waves. Wilhelm de Sitter spotted the mistake. He suggested to Einstein that he shouldn't be using this gauge if he's doing his calculation that way. Einstein complied, if you wish. And in 1916, he published his first paper on gravitational waves. And that should have been the end of story, right? Well, not quite. In that 1916 paper, Einstein had made several mathematical mistakes. Some of them trivial, but some of them conceptual. In fact, he found 3 types of gravitational waves that he called longitudinal, longitudinal transverse, and transverse. He himself was not very happy with this. he felt that probably not all of these waves are physical. By 1918, he had realized and corrected some of his mistakes. So eventually he publishes his first real, in quote, paper on gravitational waves. Über, somebody who knows German will pronounce it for me. Thank you. And there he included his famous quadruple formula of gravitational wave detection. But still, there was a puzzle on the physical nature of the waves. He was never sure that what is really the physics behind those waves. Arthur Eddington, famous names you will see all along of cosmology, etc., in 1922, shows that the first two types of waves, those two that Einstein had derived, could actually travel at any speed if you just change the gauge choices that you make. And he whimsically expressed that by saying that they travel at the speed of thought. Just think of a speed, you can tune them to travel. So that made clear that at least those two waves are not physical. But it's still, the third wave could not be done to travel at any speed. It would have to travel at the speed of light. But this still left kind of a question mark. Are they really physical or not? So that question persisted. Fast forward to 1936, when Einstein had left Germany and had relocated to Princeton. And in that year, he sent a letter to Max Born, saying, I found with my colleague Nathan Rosen, a young American physicist who started working with him, that gravitational waves do not exist. And on June 1, 1936, they submit to Physical Review a joint paper titled, Are there any gravitational waves? And the answer given in the negative. Howard Percy Robertson, another famous name, was actually the referee in that paper. He was also the colleague of Einstein at Princeton, but he was the anonymous referee. And he finds that the paper is in error. He wrote a very careful reply, explained the error, even suggested how these errors can be corrected, and the editor forwarded that to Einstein as it is the process. Einstein was absolutely incensed. He obviously was not familiar with the concept of anonymous refereeing, and he said, and he thought, I gave you a paper to publish it. What is this business? So he wrote back to the editor, we, Mr. Rosen and I, had sent you our manuscripts for publication and had not authorized you to show it to specialists before it is printed. I see no reason to address the, in any case, erroneous comments of your anonymous expert. You can see how it drips of contempt. So they withdrew their paper and they published it in some obscure journal of the Franklin Institute, published in Philadelphia. Still exists to this day, actually, this publication, who were, of course, overjoyed and all too happy to publish the paper as is. Now, Leopold Infield, Nathan Rosen, who was American, left the United States for Russia. And a young Russian physicist, Leopold Infield, came to the United States and started working with Einstein. He talked with Einstein. Einstein explained to him his ideas about gravitational waves, but he also talked to Robertson, who was a colleague there, and Robertson explained to him his views about Einstein's paper, and Infield saw that actually Robertson was right, that how do you say that to Einstein? So it basically took him a couple of years, but eventually he conveyed the idea that maybe that crazy anonymous referee might have a point, etc. Einstein was shaken, but not quite ready to concede. So right before, so when he had to actually give a talk on that, he said, if you ask me whether there are gravitational waves or not, I must answer that I don't know. Eventually, in 1937, he accepted the referee's comments. He revised his manuscript according to the manuscript that he had written with Rosen, according to the correct treatment. He published it. He said, after encountering relationships which cast doubt, that was the previous thing, eventually it turns out that rigorous solutions do exist and gravitational waves exist. And as he should, he added a note where he thanks Professor Robertson for his friendly assistance in the clarification of the original error, and Mr. Hoffman for kind assistance in translation, like two are on a par. Anyway, so that concludes the story of how gravitational waves were finally, even for Einstein, solidly established. And it's already 1937 note. Now, a question that still remains is whether gravitational waves carry energy. Of course, you may say, this is crazy. Of course they carry energy. They move stuff. They must carry energy. And that's exactly right. However, as you know, energy in general relativity is a very tricky concept. There is no global concept of energy. You cannot compare, add, or anything energies from systems that are at different space-time points. And gravitational waves are pure space-time. They don't participate in the stress-energy tensor. So in principle, you cannot say if they carry gravitational energy. Fast forward to 1957, to the Chapel Hill Conference. That was a conference that was organized to deal with the current exciting topics in physics, and it was attended by various young participants at the time, at pictures where they are young or not so young. Herman Bondi, Bryce DeWitt, Hugh Everett, Julian Schwinger, and John Wheeler. The question of gravitational wave energy occupied one full day of that conference, and it was hotly debated back and forth. How can you define a pseudo-tensor, etc., etc.? Now, another young participant at the time was Richard Feynman. Richard Feynman was a little bit impatient with these formal concepts because he wanted to see how things work. So he proposed his sticky bead argument. Assume that you have a rod with two beads that can slide along this rod. The rod is very stiff, but the bead can slide, but there is friction, so that's why they are sticky. If a gravitational wave comes, it will move these beads with respect to the rod, up and down. As they move, because there is friction, they will produce energy. That energy is stored in the rod as heat. Therefore, voila, gravitational waves carry energy. This argument, amazingly, persuaded other people. So they agreed that actually there is energy, and they just had to see how to fit it within the formalism. And Feynman's quote was, I was surprised to find that the whole day of the conference was spent on this issue and that experts were confused. That's what happens when one is considered energy conservation, tensors, etc. You know, these things, tensors. When one is considering energy, instead of questioning, can waves do work? Fine. So that was settled too, one way or another. And as it turns out, the seeds of gravitational wave detection were actually planted there. Not only because this is essentially what we do when we detect gravitational waves, but what you're going to see now. Before we go into that, let's talk a little bit about gravitational waves, their physics, their math, and their engineering. We all know that, so we will go fast. GR works in terms of the metric tensor of space-time, which is 10 components. Roughly speaking, 4 lengths and 6 angles that you need in 10 dimensions to describe the geometry of space-time. And Einstein's equations relate a geometric object, the Ricci tensor of space-time, with a matter object, the stress-energy momentum tensor. So this combination is Einstein's Einstein tensor. And there is an extra term that you can add there that you could equally well put on either side. That's why it's purple. You could either consider that it's a perfect fluid, put it over here, a perfect fluid that permeates all of space-time, or that it is an innate property of space-time, since it depends on its metric. It's the infamous cosmological constant. Linear gravity means that you have some background and you consider small fluctuations around that background, and you write the metric as the background metric. You can take it to be flat if you wish, plus fluctuations. These fluctuations are not unique because you still have the freedom to choose your coordinates, and that's like a choice of gauge for that quantity that allows you to impose 4 conditions called gauge choice conditions, and those are Lorentz-like gauge choice. You use Einstein's equations to linear order to write an equation, and eventually you obtain, if you use this modified trace inverse, we call it deviation for the metric, you obtain an equation which is exactly the wave equation in 4 dimensions. Still, when you do that, some freedom to choose coordinate remains. You fixed 4 of these coordinates, but as is customary, the equations of motion tell you that another 4 can be fixed by appropriate choices. So you have 4 plus 4, 8. You start with 10 degrees of freedom. You eliminated twice the number of degrees of gauge freedom, 4. So you are left with just 2. So these are the 2 gauge invariant physical degrees of freedom of a gravitational wave. So each plane wave carries these 2 degrees of freedom. These are the 2 polarizations. And these polarizations are analogous, although not of the same type as the polarizations of a light wave. The effect of gravitational waves, let's say a plane gravitational wave sweeping and coming through this room, is that the geodesic distance, that means the physical distance between 2 points, oscillates. And in one polarization, they would oscillate like this. I think I even have a cartoon. And in the orthogonal polarization, that is rotated by 45 degrees, they would oscillate like that. And, in a time evolution, I didn't have a better cartoon, that's what would happen. Now, it should be crucial to understand that gravitational waves have absolutely no effect on isolated particles. If you have a molecule here and a gravitational wave sweeps by, no matter how strong, the molecule would feel absolutely nothing. It would not be excited to a higher energy state. It would not be shaken in any way. The only thing that happens is that the geodesic distance between a molecule and another molecule would change. So if they were to communicate with light signals, they would detect that it would need a little bit more or less time to communicate. However, gravitational waves do have effects on bodies, on finite bodies, because if my 2 hands are at slightly different geodesic distance, the molecules that fill the gap would have to be at a slightly less smaller, say, distance between each other, but the forces between my molecules are determined by the distance. So because I'm a body with mutual forces, that would create forces on me that are of tidal forces. So that is what I have been explaining to you here. That's what happens when you have a cross-polarized plane wave traveling, and individual particles feel nothing, but extended bodies feel tidal strains and stresses. Strains are the deformations, stresses are the forces, and that's what makes Feynman's sticky bits argument work. Also, the change of distance is proportional to distance itself. It's an overall dilation in one direction and shrinkage in the other direction. And this deviation h mu nu, this gravitational wave part of the metric tensor, determines the strain. That means it's the percent change of length, if you wish. So that tells you that if you are going to measure these changes of length as part of your gravitational detection experiment, you need very large strains, which are hard to produce, or very large distances, so that h times the distance gives you a large deviation. All right. Let's also talk a little bit about the generation of gravitational waves. Gravitational waves are produced by accelerated masses, just as electromagnetic waves are produced by accelerating charges. But in fact, it is the quadruple of the distribution, not the dipole of the distribution, that enters into their production formula. There are no dipoles in gravity, and the monopole does not radiate. So it is this quadruple tensor that enters Einstein-Eddington's quadruple generation relation. And the formula looks like that. The strength of the gravitation is proportional to the second time derivative of that tensor, retarded because the wave takes some time to reach to you. So as it was when the wave was produced. You can also see that the total gravitational wave luminosity, that means the total energy produced per unit time by such a body, is a time average of the triple time derivative, the square of the triple time derivative of that quadruple thing, which compares again to electromagnetism. It's a very similar formula with different constants appearing. Third derivative, but now with dipole moments, not quadruple moments. Now, these factors here that appear in this formula and that formula are incredibly small. So you see that you need very large dipole, very large quadruples, and fast changing. Now, large quadruples means highly asymmetrical bodies with large masses and large dimensions, hard to come by in space where most things are spherical. And fastly moving means that they have to really change fast. Again, stellar or cosmic bodies move rather slowly and gingerly. So you see that it's a very good approximation, because already the zeroth, the first order gravitational production is extremely small and everything. Only when you have collapsing black holes, you really cannot use that formula and you have to go to the full general relativity. In any other instance, even collapsing neutron stars, it's a very good approximation. So let's do some order of magnitude estimates. What's big, what's small? You can do essentially dimensional analysis, see how these things scale. So the quadruple scales with the total mass and the square of the dimension of the body. Again, you can have a sphere for which Q would be 0, but it would be some coefficient, big or small, times this. Second derivative would scale like that over the typical time, the period of motion of that body, which is like the typical mass times the typical velocity, and that changes like the typical mass times the typical velocity cube over the size. So in general relativity, we define the geometrized mass, which is simply the mass measured in unit lengths once you put G and C equal to 1, or equivalently, you leave them there and you define this geometrized mass. In those units, the geometrized mass of the Sun is about 1.5 kilometers. What is that? It's actually the size of the black hole that this mass would form if it were to collapse into a black hole. And in gravitating systems, you know from the virial theorem that you basically have that V square is of the order gm over r. If you have masses self-gravitating, that's the order of magnitude of their velocity square. You put everything together into your formulas, and you find that the strain is of the order of the gravitational mass squared over the size from the source times r. And the total power, you'd actually get a formula that contains a universal constant here, times the ratio of the gravitational mass of the producer over its actual size. The gravitational mass is a size, for the Sun 1.5. The actual size is much bigger size. And you say, oh, goody, this is a huge number, because this is 10 to the 52 watt times this number. Problem is that this is a tiny number for all practical situations. So although this is huge, the total power emitted is actually like this, right? And therefore, this tells you that, yes, there may be a lot of power produced, but by the time that it reaches Earth and it is attenuated according to the inverse square law, it's going to be pretty weak. That means that in general, if you look at this formula and also that formula, we need very compact bodies in order to have substantial production. We need bodies whose size is as close as possible to their gravitational size. That means that if we are to have a fighting chance of detecting these waves, these bodies have to be either collapsing black holes, the most dense object in the universe that still has a quadruple moment, a pure black hole has none, or at the next level, collapsing neutron stars, extremely dense bodies and small in size, that as they collapse in the final stage of their collapse, they come very close to each other. So these are the only two situations that we can hope to see gravitational waves. But what would we actually feel here on Earth when the waves come? Well, they are changes of length, so we would see length changing. Let's see what we expect. Let's take a very optimistic scenario, the best scenario possible. The nearest one would be a little bit outside of our solar system at the scale of nearby stars, let's say 10 lights away. And assume that this is something that involves black holes of the order of a few solar masses collapsing. And for black holes, the gravitational and the actual size are of the same order. And you put that in your formula, and it gives you a strain of order h of 10 to the minus 13. So if you had a rod of a length of 1 meter, that gravitational wave would change that about to the 10 to the minus 14 meter. And that's the size of a typical nucleus. And now, this is an incredibly lucky event where you have black holes collapsing literally next door to you. Our galaxy is billions of light years in size, and you say, oh, there's one right next door. So this is not going to happen. A less ideal source, a typical source, which is not black holes, but say it's a supernova, at a typical position in our Milky Way, would give you a strain of the order of 10 to the minus 22. So even if you had a beam of length 100 kilometers long, the length of that beam would change by approximately 10 to the minus 17 meter. That is substantially smaller than the size of a nucleus, substantially smaller than the size of a proton. So what are we talking about? Moreover, since it's so small, such changes of length would be completely drowned into quantum mechanical fluctuation effects, uncertainties in position. In other words, to state that in a scientific term, are we crazy? Apparently, some people were crazy and they took all that seriously and they proceeded. Now, frankly, if you had shown me this and said, now we want to detect its gravitational waves, I would say, okay, fine, good luck. See you later. Well, some people took up the challenge. So, let's talk about crazy, really crazy. In that famous Chapel Hill conference with gravitational waves and the Feynman argument, there was a participant, Joseph Weber, who was actually an engineer, but he was an expert in building resonant cavities, etc., and he was interested in physics. So when he heard about gravitational waves, he had an idea. He would detect them. How? You form a mechanical resonant cavity, and that resonant cavity has the property of actually amplifying waves. The math is very simple, and it's based on this that you teach in undergraduate courses, that if you have two masses with a spring and some friction, of course, some dissipation, that's the equation that they obey. And if you excite these masses with an external force or an external vibration, the energy will build up in this oscillation until the extra energy that's coming from the external force is balanced by the energy dissipated. And it turns out that if you drive that to resonance, that means the frequency of the excitation is the same as the natural frequency, you can amplify that by a factor of Q, where Q is the quality factor. Q increases or decreases as the dissipation increases. It's roughly Q as a number, it's a pure number. How many oscillations should this oscillator do before it dissipates 1 over E of its energy, roughly speaking, like that. Now, you can make that Q in very good constructions to be thousands, actually, and that's what Weber thought of doing. So he built this bar detector. It was basically an aluminum cylinder that vibrated because of its own normal modes. We had some piezoelectric crystals there to detect that vibration. These are the technical characteristics, but he achieved a Q of about 200,000, which is very good. So he put it to work, and he claimed that the only limiting factor in the performance of his detector would be thermal fluctuations, so that was the limit. He put it to work. It took him about 10 years, and lo and behold, he observed gravitational waves. So in 1969, Weber claims that he detected gravitational waves. That was exciting. There was only one small problem. He detected lots and lots of these waves. Well, where is the problem in that? The problem is that these waves would need to come from somewhere, and from the way that they seem to be emanating, they should be coming from somewhere within the galaxy. So something within the galaxy, say black hole or stars within the galaxy, should be producing that much power in gravitational waves. It turns out that if the galaxy were to produce that much energy in gravitational waves, such that Weber would detect them, the Milky Way should have shed most of its energy and then dispersed long ago. So Weber's results were not credible, but still they created a lot of discussion and excitement. If he was crazy enough to do it, maybe somebody else could do it right. Weber actually received several prizes for that, not because he detected gravitational waves, but because he had the wherewithal to try, and even with a crazy effect, motivate other people to do the work. Sometimes you have to do that. And then a note came from the sky. That's the famous Hulse-Taylor Binary Pulsar. Pulsars, as you know, are double stars, one of which is actually a rotating neutron star that produces a torch of gravitation. And if we are lucky enough that as it goes around, we are at the path of this torch, this beam goes through us periodically as these double neutron stars rotate, and that we detect that as a pulse of electromagnetic waves, radio waves usually, that we call a pulsar. And they are very fast. They have frequencies that can be more than 1 hertz. So they go like tuk, 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 tuk. Now that doesn't sound very exciting, but imagine that you look at the sky, far deep into the galaxy, and you hear tuk, 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 tuk. What do you think? Could it be a stellar, could it be a cosmic body? It would need to be something that pulsates at the rate of once or twice per second. No bodies of the size of the sun or planets do that. So the first guess would be, oh, these are extraterrestrials sending us signals. It turns out that these are real systems, these neutron stars, that because they are so compacted, so near each other, they do rotate around them like crazy. So it's an exciting physical object. But these two guys, Alan Russell Hassel and Joseph Taylor, discovered a double neutron star pulsar, and they monitored the frequency of its pulsation. And they found that that frequency increased slightly, it decreased slightly with time. Slightly, but measurably and perceptibly. After they accounted for all possible other factors that would account for, that would produce this slowing down, they ended up saying that the only possibility, the only remaining possibility was that they are slowing down because they are emitting gravitational waves, therefore their energy decreases, their distance increases, and their frequency of rotation decreases. So they made some precision measurements of the periastron time for several years, compared to GR calculations, and lo and behold, the calculations agreed perfectly with observations. Complete agreement. I'm sorry? You just have a radio telescope, and you hear these pulses, tuk, 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 and you monitor how they evolve within a few years. So they rightly received the Nobel Prize for that. Now notice that the Nobel Prize they received in 1992. 1992 is here. So by that time, only this part of the measurement was already obtained. And later, other measurements were obtained. It's quite likely they still fit the curve, because it had been rather embarrassing if after the prize they started doing that. But okay, they didn't. So that is a signal, that's a note from the sky, that yes, gravitational waves do exist after all, and they do carry energy, just as you humans think, but you can't feel them because they are so weak. So now we enter the new era, the large-scale interferometry, and we jump to 1975 to the NASA meeting on space research in Washington, D.C. There, we will focus on two participants, this guy and that guy. We've seen them before, if you remember. I don't know, I don't have the cartoon here to remind you how they look today and how they were then. The comparison is quite interesting. This is Ray Weiss, who was then a young postdoc or faculty member at MIT. And this was Kip Thorne, a young but already quite eminent general relativist theoretical physicist in Caltech. They actually had to share a room, because apparently at the time, physicists of any age were okay to share rooms. And I know that some of you guys are okay with it, but some people of my age might not be comfortable with the concept, but these guys were perfectly comfortable. In fact, Rainer went to the airport to drive Kip to the hotel. And because they were both interested in the question of gravitational wave detection, they ended up spending the night talking about it and planning. And if I know anything about Kip Thorne, sorry about that, if I know anything about Kip, I am pretty sure that substances were also consumed during that night. So Weiss had already proposed an interferometric method for detection of gravitational waves and had built a toy model, a prototype at MIT. Thorne was interested in that. He liked the concept very much, and he decided that actual interferometry is the way to go. So on his way back to Caltech, after they had made several plans, he set out to persuade the administration to do it. The principle, of course, is the standard interferometry. I'll again a few words. You have a laser beam that is split through a half-silver mirror into two beams. They go in orthogonal directions. They bounce off a mirror and come back, and they recombine at the same mirror into a single beam that then is detected by a detector. If the paths they travel have exactly the same length, down to a fraction of the wavelength of laser, then they will cohere, they will interfere coherently, and the detector will detect a strong signal. If, however, their paths differ by half a wavelength or a fraction, they will cohere distractively or partially distractively, and the detector will see an attenuated signal. So, by monitoring the strength of the signal, you can detect minute changes in the lengths, which is double that distance of those two arms. So it's a very sensitive way of measuring lengths effectively. That's where the idea of the LIGO detector were born. There are many improvements to this concept, but that's the basic idea. Here's what happened now from the actual human point of view, because, you know, to do science, you need, of course, good ideas, but you also need the resources, and the resources means grants and administrations willing to support you. So Thorne recruited the experimentalist, a Scotsman, Ronald Drever from Glasgow. He actually came to Caltech part-time and then full-time from 1983 to build locally at Caltech, actually not at Caltech, but around Los Angeles in the Mojave Desert, the gravitational wave detector, while independently but collaboratively, Rainer would try to build his prototype at MIT. The problem was, so actually Trevor did build, he was an expert in that, did build an interferometer at the Mojave Desert with a 4-meter arm length. Now, here's the problem. The National Science Foundation would only fund one big project. So when they submitted their proposals, both of them essentially proposing the same thing so that they can do it independently, they said, no way. You have to do it together or nothing at all. So they basically ordered them to collaborate. So the Caltech MIT LIGO project was born, and it was jointly led by Drever, Thorne, and Weiss. Pretty soon, when you have a collaboration like that, like in life, like in marriage, like in everything else, strifes started appearing, and especially between Drever and Weiss. Remember, they were the two experimentalists. They had competing and sometimes incompatible ideas on how to proceed. Thorne did his best to mediate, but they couldn't really put it together. By 1996, NSF was exasperated and basically ordered the dissolution of the leadership team, telling them, none of you three guys are able to carry out this project. And they appointed Rochus Vogt as the sole director. Surprise, I also took a course from this guy. Very difficult fellow. I'm saying that because as hard as Rochus tried to make the team work, eventually it didn't work. The project was funded in 1990, so that was a surprise, but eventually Vogt stepped down, and another fellow, this one, Barry Barris, became the new director. Now, what was Barry Barris' specialty? Experimental elementary particle physics. I guarantee you he didn't know how to write down a gravitational wave. So what was his qualifications? He was very good at organizing large projects. In elementary particle physics, you have these big collaborations, as you know, and it's not enough to know the physics, it's to know how to collaborate the various parts, both in physics, engineering, and also human resources that collaborate for the project, and how to keep it running. And he was very good at that. So he introduced some new concepts. He conceived, first of all, LIGO as a modular incremental project progressing in stages. His idea was that, look, if you try to build the whole thing and you have a plan that you will build it in 5 years, it will probably be built in 20 years. By that time, the funding agencies will lose patience. So you have to do incremental steps to show that you deliver, to have something to present, to learn from your mistakes until you do the next thing. It might take you a little bit longer overall, but you will be making progress and you will keep funded. And that was crucial, apparently, for this project. He created the LIGO scientific collaboration. He was used to international collaborations, being a particle physicist working also at CERN, that also involved groups in Europe, and especially this alliance with European collaboration, Virgo in Italy and the GEO 600 in Germany. These are smaller detectors, this one slightly smaller than LIGO, this one substantially smaller, but it was good to have these general detectors progressing simultaneously. Finally, the project flourished and LIGO came alive. So that's how LIGO looks. It's 2 detectors, one in Hanford, Washington, and the other identical in engineering terms in Livingston, Louisiana. They are some 3,000 kilometers apart. They work like 2 eyes of a bivisual thing, because by measuring the relative time delay between the signals that they would detect, we can have some idea of where gravitational waves would come from. As engineering objects, they are quite astounding. They came up in stages. The total cost was in excess of $1 billion, which means that they were essentially free by big project standards, very small amount. The length of these tunnels, this legs, is 4 kilometers each, but because they are doubled and because they also use some kind of resonant cavity techniques, the effective distance increases to about 100 kilometers. The pressure inside the tubes is 1 over that fraction of an atmosphere, absolutely crucial so that the laser beam not be disturbed as it travels, several times actually. And it can measure distances down to 1 over 10,000 of the size of a proton. That's absolutely amazing. It is the most accurate measuring device ever built. And of course, you may say, what happened to that thing about being drowned in quantum fluctuations? Anybody has a guess? Well, what happens is that indeed, each individual nucleus or atom that reflects this beam fluctuates with a much, much bigger uncertainty than this number. But what is relevant is the collective position of all these atoms or molecules forming the mirror. That collective position of the mirror fluctuates with a much, much lower uncertainty. And it turns out that after it gives you some noise, the fact that you have atoms fluctuating gives you some noise, thermal noise, etc. But it's the average position that determines the shape of the signal. And that hits the quantum limit. I mean, that quantum limit is much smaller. It's a very sophisticated machine. I don't want to bore you with all the details. There are a dozen of possible sources of errors and noises. You can read the obvious ones being thermal noise, gas noise, but there are seismic vibrations, somebody stepping next to the machine, all that is there, etc. All these noise are kept in control by an elaborate suspension system, cooling down, high vacuum, etc. And the machine has a sensitivity as a function of the frequency of the gravitational wave. It's not too sensitive to frequency because it's not a resonant cavity, but it still has a response like that. And that was phase 1, that was phase 2, and that's the future one. And it can measure an H better than 10 to the minus 23. Pretty damn good, I must say. Of course, Europe, as I mentioned, was not still. Alain Briet from Orsay and Adalberto Iazotto from Pisa, who passed actually recently a few months ago, put together the collaboration that became eventually Virgo in 1989. And not to make the story too long, it was eventually approved by CNRS, then by NFN, etc. And it comprises about 178 physicists, and they built their detector in Cassina near Pisa. It's slightly smaller, 3 kilometers than LIGO, And they started observing as well with very low sensitivity in 2007, then advanced Virgo in 2011, and became fully operational. Look at this date, August 1, 2017. You will see why. More than 300 people from 19 laboratories within Europe participate in full collaboration with LIGO. Germany is also in the game, as I told you. It's a much smaller detector. It's about 600 meters long. So one would ask, what's the point of doing it? I asked people, and they said that it's a very good proof of concept. Even though they don't hope that they will really detect substantial gravitational waves, what they are doing proves several concepts in this business that have been valuable. So it's really an international effort. Yeah, because one of them didn't quite sign up, but he decided to collaborate, so okay, I can give you more details, but that's the story, right? And finally, because most of us in here are theorists, I think I should say something about theory. Of course, theorists were not just sleeping all the time, they were hard at work, because general relativity is a very hard subject. And it's not enough to have the linearized approximation, what you asked me just a quadruple moment. What you've hoped to see is gravitational waves from rotating and merging black holes, and you cannot use any linearized theory there. You really need the full machinery of general relativity. And therefore, we need both theoretical tools and numerical methods. In theoretical tools, I would mention this triad here, Arnowitz, Deser, and Misner, who derived the famous Hamiltonian formalism of GR. And that's theoretically important, but it was also important for numerical studies because it works in terms of initial data, and that's crucial for numerical studies. And also Thibaut Damour in France studied theoretically binary systems, calculated using various techniques the waves emitted from double collapsing stars beyond the linear approximation, effective some theories that, again, they helped people do numerical calculations. And of course, these are the unsung heroes, the numerical relativists, too many of them to give credit, but they are really the ones who made the wheels turn and developed numerical methods that could compare experimentally observed signals with theoretical predictions. So now we should be ready. And we are almost out of time, but you are free to leave at any time because we haven't quite come to the punchline yet, right? That's the famous chirp from outer space. So, we're talking Sunday, September 13, 2015. That was 4 days before the official start of advanced LIGO. The official day was 4 days later, but by that time LIGO was fully ready and in so-called engineering mode. Engineering mode means all systems are running, but officially we are not observing. That's what it means. It's kind of like a prova generale. Now, Sunday night on that day, some last-minute tests were done with detectors, or they were burning the midnight oil, as they say, until at about 4 a.m. Monday, LIGO still emitting signal. That's the exact time at which it happened. Again, all these noises are from 2001, right? So that was something that was detected first at LIGO on the East Coast in Louisiana. That signal lasted about 0.2 seconds, and it was recorded by both detectors with about 7 milliseconds difference. The first thing that they checked was whether this was a test. Did you do something? No. Did you do something? Did somebody else do anything? Did some automated system produce that? After they checked everything to regain sanity, they realized that no, that was a real signal. Now, that signal was almost identical in the two detectors, and it came with a time difference of about 7 milliseconds, which is order of magnitude the distance between the two detectors in light units, the amount of time that light would take. So, it's something that is exactly the same on the two detectors, 3,000 kilometers away, and with a time difference of light. So it's something clearly of the time of flight of light. So it's clearly something that came from space and ran with the speed of light. What else could it be? Well, not a test signal, not Earth-generated. You could not get it exactly the same on those two detectors if it is Earth-generated. So that's the thing. That's the thing that gave the metal. And that's the actual signal that you see here. And that is the signal first in a raw form and then in cleaned up form after noises, etc., were filtered out. You see how similar it is between the two detectors. So everybody was sure that this is a gravitational wave. Of course, you don't go out and announce we found it. You have to be certain and certain and certain again. So they announced it several months later, on February 11, 2016. You know the story by now. Comparing with its strength and shape with numerical general relativity calculations, they figured out that this must have come from something at a distance about 410 megaparsecs, about 1.34 billion light years away. It was from two merging black holes with 36 and 29 masses of Sun, and the final mass is 62. So you see that about 3 solar masses worth of energy were turned into gravitational wave energy that was emitted away. And the signal that they received is good to 5.1 standard deviations, which is the gold standard of 5 sigma. So at that point, they were completely certain. That means that if you were to continuously observe with your detectors and detect whatever is coming, the chance that this signal would have been produced by sheer chance would be less than 1 per 200,000 years. So we call that practical certainty. So that's the event that produced it, and here is a simulation of the merging of the two black holes. This is not a cartoon, this is an actual simulation in real time. That is what happened in seconds as we understand them here. Okay? So that was a great, exciting discovery, but of course there are always a few skeptics. The first is, didn't it come too early? I mean, you just turn on your machine in engineering mode and you're not quite ready yet, and poof, here it comes. And exactly on the 100th anniversary of Einstein's general relativity, are you sure? It's a bit suspicious. Were there some cosmic forces conspiring to give Einstein a present for his birthday, or what? But if this is really a signal and you saw it immediately after you built your detector, that means that there are many such signals happening, because otherwise it would be incredible that there is one now and another one in 10 years, and you just happen to be there to see it as you came into business. And you should see these many more signals soon, or else we won't believe you. And indeed, they did. Several more were detected. I list here a few. In 2016, LIGO went upgrades, but then it became operational again. That black hole was already detected before they announced the first one, but because the signal was not that good, they decided not to make a big deal out of it. But then 2 more black hole events were seen with very good statistics, and this last event was finally seen by Virgo. So Virgo actually missed the chance of seeing the first gravitational wave along with LIGO by a few months. But, well, somebody has to do it first. So it's clear that black hole mergings happen very often, quite often, and they shower us with gravitational wave showers or chirps that we can detect. That's fine, but can we hope for a different item in the merging? I mean, how many chirps can you receive and still be excited about it? We saw them, we verified them, we hope for something else. And I don't know. Let's see. Okay, good. So then we come to the famous GW 1708-17 event, which was a fist of the discovery. Gravitational wave detections, in a very obvious way, receive a code, GW, for gravitational wave, the year, the month, and the day. Surprise. So, Thursday, August 17, 2017, at 8:41 Eastern Time, that was after the first detection, a qualitatively new signal was received. And it was qualitatively new because it had a broad frequency band. It sounded like that. And it lasted, let's play it once more. There it is. and it lasted almost 100 seconds. This is how it sounded in actual real time for the last few seconds. Not only that, but it was detected by LIGO. Unluckily, but not unhappily, it was not detected by Virgo. But also NASA's Fermi Space Telescope detected a simultaneous burst of gamma rays. So take these events together. We receive a gravitational wave, LIGO, Virgo doesn't, but NASA's Fermi Space Telescope detects at exactly the same time, within the light distance between the observations, a simultaneous burst of gamma rays. That means that those must have emanated from a single event in space. And see if it works well. So the only thing that could have produced such a thing was what we call a kilonova. What's a kilonova? The name says. It's a supernova that is 1,000 times more powerful than the typical kilonova. A typical supernova is a collapsing and an exploding star. A kilonova, to produce that much energy, must be two rotating and inspiraling and eventually collapsing neutron stars. So they put everything together and they identified it as a double neutron star of 1.5 sun masses each at about 130 million light years away. That's what LIGO observed at Hanford, Hanford, Louisiana, and Livingston, Louisiana, and Hartford, Washington, yes. And that's what Virgo observed, which is nothing. Now, why do I say that this was fortuitous? Because Virgo by that time should have been able to detect it. It's just that Virgo had a blind spot in the sky, had actually a blind region. So if Virgo did not observe it, that must mean that the signal was in that blind region. From these two observations, you can draw an arc on the sky. If you have two eyes looking and you detect their time distance, that draws basically an arc on the sky where the signal must have been. You cross that with a double point of Virgo and it gives you a region. And then you go to astronomers and tell them, in that region, try and see if you see anything new. And you also had that signal at the Fermi Space Telescope. And yes, astronomers trained their telescopes there, and within hours, they had observed a new star, which was the kilonova. So everything fit exactly and precisely. Sometimes not seeing things is better than seeing them, or just as good as seeing them. So about 70 Earth and space-based observatories saw it. The position was determined with great accuracy because it was optically kind of determined. And what's special about kilonovas is that they emit a very broad spectrum of electromagnetic radiation, but also lots of other stuff. Neutrinos, for one thing. Black holes don't emit any of that. And matter. In fact, they emit also heavy elements that are produced in the final violent phase of that event that includes gold and platinum. In fact, not even supernovas are violent enough to be able to fuse nuclei so that they produce these heavy elements. All the gold that we have here on Earth, highly valued and appreciated, has come from such kilonova explosions that ejected them. It was recycled into galaxies, nuclear systems, and some of that ended up with ourselves. So it was really a gold event, if you wish. Let's see if that will work. That's an actual simulation of the inspiraling of those waves, and that's what they emit. That's a blow up of that region. It's not so interesting. What is interesting is that this is real time and the actual simulation. And at the final phase, they emit all that stuff, matter and neutrinos. All right, good. So we are done, but where do we go from here? This is really the dawn. I mean, we are all interested in our own field, etc., but we should appreciate that there are some fields that are on the verge of great progress and discovery, and we are really at the dawn of what we call multi-messenger astronomy. We can combine gravitational waves, electromagnetic waves, including light, and neutrinos, so that we can make more discoveries or more accurate observations on events that happen in cosmic physics. It's as if we have new pairs of eyes. We could only see in that kind of stuff before. Then we added the vision of neutrinos, not very sharp, but still useful. And now we added the vision of gravitational waves. So we expect a lot of interesting developments in astronomy in the years to come. There are, of course, new gravitational wave detectors that are to be built. There is a new LIGO here in India, and one called Kagra in Japan. There are some ambitious projects. One of them is space-based. These are beams, actually. It will be a space-based, these are not beams, these are triangles, and there are several such triangles rotating around and communicating with the laser beams. So that's effectively like a huge gravitational wave detector that will have a baseline, not 4 kilometers, but 1 million kilometers, so that will be great. And its expected launch is around 2030, which means that you should expect it around 2050 or so. And there are some Earth-based projects, one of them being the European Union Underground Einstein Telescope project that will be hanging isolated from most vibrations. It will be 10 times more sensitive than LIGO at fractionally bigger cost. So we are really at the dawn of gravitational wave astronomy. That was basically my take, and this is some motivational stuff that is particularly useful to students, but also to us. Let's not forget what it took for all that to happen. Of course, it took vision, it took optimism, enormous optimism, theoretical excellence, technical ingenuity, wise leadership, persistence, years and years of persistence, superhuman hardiness against adversity, hundreds and hundreds of brilliant scientists and engineers, wealthy, nimble, and determined institutions, courageous funding agencies, and also the political will to support fundamental science. And that's also a commodity that we need in science that is recently in short supply, and we should not forget that it is needed. In fact, it took the whole world to do it in one way or another, and probably it will be listed as one of the great collaborative projects of science and of human history. Well, that's all I had. Credits and thanks to all these places where I got information or movies, etc. Some people that I talked, etc. And your patience and indulgence in this talk. That was it. Thank you.
Questions?
In hindsight, do you think that Feynman's sticky beat argument works? Was it correct? Because I'm thinking that the gravitational wave could also make the rod expand, so the beads might not actually have any friction.
The rod, remember, these are physical objects. That's why I stressed what happens to individual particles, which is nothing, and what happens to bodies, where particles interact with forces. The rod is made of a very stiff material. So although gravitational waves would like to make it change length, it does not, because the forces do not allow it. The sticky beads, however, are free to change their position because there are no forces between them. So the argument actually does work exactly as it was stated.
More questions?
The signal started before the dawn of man.
I'm sorry?
The signal was generated before the dawn of man.
Way before. Way before the dawn of man, indeed. If that has any meaning, right? Because simultaneity is...
So I have simple questions. That sensitivity 10 times more means there will be 1,000 more events, the frequency of events?
Say again?
You said that the new generation of LIGO will have sensitivity 10 times more sensitive than no. It means how scaling works. It means 1,000.
Well, I don't know the answer because, of course, that has to do with the distribution in power of these events. So you have to move by a factor of 10 and see what is the events that you would be capturing. And I don't know if it's a power law or what it is.
Well, I'm just thinking simply because if 10 times more sensitive means the radius can be 10 times bigger, means volume.
Right. If
1,000.
from the same events, the radius could have been 10 times bigger, but it could also detect within that radius 10 times weaker events. So there is an overall scaling. Part of it is exactly what you said, the increased range, but also part of it is what is exactly the distribution of those black hole merging events.
Questions? Okay, let us thank Alexios for the great talk. Thank you.